Okay, good morning, everybody. This is chapter 18, acid-base equilibria. Um, for the first few sections in the chapter, we're going to have to basically define some basic terms and concepts that we need to use for the later parts of the chapter. So the first and foremost definition of acids and bases are extremely important, and then we're going to proceed to other concepts like conjugate acid-base pair, the other types of definition of acid bases that are important, and we will take a look at them as well. So let's start with the acid-base definition. This is the Arrhenius acid-base definition. Um, Again, we will look at another type of definition, which is called the Bronsted-Lowry definition later on. But this particular one is called Arrhenius acid-base definition. According to this definition, acid is any substance with H in its formula, and it dissociates in water to yield H plus or H3O plus. Please note that throughout the chapter in your textbook, the author uses H plus or H3O plus, which is called the hydronium ion, interchangeably. So anytime you see H3O plus and H plus, their concentrations are equal, so you can assume they are the same. So H plus, H3O plus, the same thing. A base, according to Arrhenius acid-base definition, is a substance with OH minus in its formula, and well, I should say with OH, not OH minus, in its formula that dissociates in water to yield OH minus. We will take a look at some specific examples of the acid-base definition of Arrhenius. Now, when the acid reacts with the base, they undergo what is known as a neutralization reaction. A neutralization reaction occurs when the H plus from the acid reacts with the OH minus from the base to form the neutral molecule, which we know as H2O. So in that sense, since the reaction leads to the formation of a neutral molecule, H2O, it's called a neutralization reaction. Okay, now the variation in acid-base strength is something that we need to consider when it comes to the concept of acid and base equilibria. Because all the acids that we have, whether they are weak or strong, and also the bases, their strength is defined with respect to the extent of their reaction. So, for example, strong acids and strong bases, they dissociate or react completely into ions, and they are therefore considered to be strong electrolytes. So anything that reacts completely is considered to be a strong, whether it's a strong acid or strong base. On the other hand, weak acids and weak bases, they dissociate slightly into ions or partially into ions instead of completely, and therefore they are considered to be weak electrolyte. So one more time, strong acids, strong bases, they react completely and they are strong electrolytes. Weak acids and weak bases, they react slightly or they dissociate slightly into ions, and therefore they are weak electrolytes. So as you can see, the extent by which they dissociate, whether they dissociate completely or partially, that's the basis of the definition of a strong acid, strong bases, or weak acid, weak bases. Now, when it comes to weak acids and weak bases, we usually have equilibrium established for those classes of compounds. Um, so, and this is probably a good place to mention that for strong acids and strong bases, the reaction goes to completion. Therefore, there is no equilibrium. We only have equilibrium for the case of weak acid, weak bases. So this is important to remember and distinguish from the case of the strong acid, strong bases. So now, for example, if HA, which is a notation that your author is using in the textbook, and I'm going to stick with that notation, if HA is a typical weak acid, then the ionization or the dissociation of that acid in water can be written as HA plus H2O going to H3O plus and A minus. Now, the H3O plus, of course, on the right-hand side is formed because HA is an acid and it releases a proton or donates a proton to water. Water accepts the proton and it becomes H3O plus. And of course, HA, which is the acid, has lost the hydrogen ion, so therefore it becomes A minus. Or from now on, instead of indicating the water in the reaction, we just simply ignore it and we just write it as a complete dissociation reaction without the presence of water. But it's implied that water is there. So we can write this as HA going to H plus and A minus. So that is a typical weak acid dissociation reaction. And of course, I forgot to put the reversible arrow here, but this is supposed to be a reversible arrow right here. So we have another arrow going back to HA because this is a weak acid, so therefore we have to have equilibrium established for that, and we show equilibrium, of course, by the reversible arrow. Okay, now in the next slide, I am writing basically an equilibrium constant which is called Ka for that typical weak acid reaction. So HA going to H plus and A minus. Now that can be written, its equilibrium can be written as Ka equal to H plus A minus divided by HA. Now remember, H plus A minus HA, all these concentrations, they refer to the equilibrium concentrations of these components. Now, your author may write the same Ka expression as H3O plus A minus divided. So as you can see, H3O plus and H plus, they are basically the same thing. So from now on, I'm just going to stick with H plus instead of H3O plus, okay? But just in case you see H3O plus in the textbook, don't be alarmed because that is the same as H plus that I'm writing here. And again, all the expressions in the Ka are equilibrium concentrations. Now, the Ka by itself is called the equilibrium concentration for the weak acid dissociation. Okay. Now, we can always think about a strong acid having a higher concentration of H plus in the solution when it dissociates, and therefore a larger Ka. And for the weaker acids, we can consider them to have lower percent dissociation. That means the concentration of H plus that they are going to release is going to be lower. And therefore, since that is going to be lower, the Ka is going to be smaller. So in other words, we can always go back to this reaction and see that for a strong acid, this H plus concentration is higher compared to the weak acid, and therefore this Ka, the magnitude of Ka, is larger. For the weak acid, the H plus concentration is lower, therefore the magnitude or the value of the Ka is smaller. And that's what we are summarizing basically at the bottom of the page, that for strong acid, the H plus concentration is higher. For the weak, the H plus concentration is lower. The percent dissociation basically refers to the amount of H plus that is being dissociated compared to the original concentration of the acid. Now, let's move to the next slide. Actually, I think the next slide is going to be this one right here. Okay, so now one thing that I'm asking you to do is to memorize the list of a strong acid and strong bases. It's very important to know the list of a strong acid and a strong bases. Now, there's a table on page 165 in your textbook, table 4.2, which gives you the list of a strong acid and bases, and I'm going to summarize that for you here. So the example of strong acids, and these are taken from that table, are HCl, HBr, HI, HNO3, H2SO4, HClO4. And the example of strong bases, LiOH, NaOH, KOH, RbOH, CSOH, calcium hydroxide, strontium hydroxide, and barium hydroxide. So as you can see, the first row refers to the group 1A metal hydroxides, and the second row refers to the group 2A metal hydroxide. So as you can see, the group 1A, group 2A metal hydroxides, some of them are considered to be strong bases. Now, the reason I'm asking you to memorize the list of strong acids, strong bases only is very simple, because anything that is not in this list is considered to be weak, whether it's a weak acid or weak base, okay? So all you have to do is to memorize the list of strong acids and strong bases, and anything else, you should think of them as weak acid, weak bases. Okay, so the next concept that we are going to look at is called autoionization of water and the pH scale. Autoionization of water refers to the reaction of water with itself, according to this reaction here. So the water reacts with itself to form H3O plus hydronium ion and OH minus hydroxide ion. Now, I told you before that H3O plus can be considered as H plus, so I can rewrite this reaction as just simply, because one mole of water reacts with another mole of water, so I can just think of it as water itself. Doesn't matter how many moles do we have in there, it's just water. So water dissociates into H plus OH minus, which is a familiar reaction that we already know, and this reaction now is basically what we refer to as the autoionization of water. Okay, so it's a reaction of water with itself. Now, what's important about this reaction is the equilibrium constant for this reaction, for the autoionization of water. Now, the equilibrium reaction for that is basically what we call the water ionization constant, or Kw. The Kw, if you write the Kw for that, W stands for water, and the K is the equilibrium constant. So basically, this is the water ionization constant, or ion product constant. Sometimes they refer to it as ion product, because it's a product of H plus and OH minus. So the Kw can be written as H plus OH minus, but please note that the concentration of water is not included in that Kw expression, because the concentration of water, the equilibrium concentration of water, is around 55 molar, and it's basically constant. The concentration of water doesn't change, and since it's a constant, it doesn't change. We can basically absorb it into the Kw and just basically ignore it from the equilibrium expression. So usually when we have a pure liquid or a pure solid, for that matter, in the equilibrium reaction, we tend to ignore that when it comes to writing the expression for the equilibrium constant. So pure water is not included in the reaction of the Kw, and that's why we don't have it in the denominator of the Kw expression. So we just have the product on the right hand. In other words, only the aqueous components are included, not the pure liquid. Okay. Now, so the important thing about this Kw is that based on experimental evidence, we know that the concentration of H plus times OH minus, which we call Kw, is a constant, is 1 times 10 negative 14 at 25 degrees Celsius. The reason I've written 25 degrees Celsius in parentheses is because all Ks, whether they are Kw, Ka, or any other equilibrium constant, is temperature dependent. As we change the temperature, this number is going to change. So this is only true for 25 degrees Celsius. Okay, so let's memorize this equation, which I'm calling equation 1. Okay, equation 1. So that's the ion product constant for autoionization of water being 1 times 10 negative 14. All right, now this brings us to the pH scale. pH, as I'm sure many of you have seen the expression before, and you know about pH scale based on the acidity or basicity of a solution, is defined to be the negative logarithm of the concentration of H plus. Mathematically, it is written as negative log of H plus concentration. So it's a logarithmic scale. That basically means that it's a negative logarithmic scale. That basically means as the concentration of H plus increases, the pH will fall. So there's an inverse relationship between the H plus and the pH concept. So we also need to memorize the equation for pH, or negative log of H plus. So H plus, remember, refers to the concentration of H plus in units of molarity. So it's the moles of H plus divided by liter of solution. Okay. Now the POH scale is used to refer to the concentration of OH minus in the solution for basically for most base reactions. So the OH minus concentration can be expressed as POH. POH is a negative log of OH minus, or negative logarithm of OH minus. Again, inverse relationship between OH minus concentration and POH. And I also want you to memorize this equation. Okay, now, again, as a matter of notation, we are going to write the pKa as the negative log of Ka. So from now on, when we write pKa, what we mean is the negative log of Ka. Remember, Ka is the acid dissociation constant, and usually referring to a weak acid dissociation. Okay? So when you take the negative log of Ka, what we get is pKa. So this will save us time, and also many times we are going to use it in chapter 19 for the calculation of pH for a buffer reaction. So let's just be familiar with this notation that the negative log of Ka will be noted as pKa. Now, the relation between pH and POH can be expressed as this equation 5, that the sum of pH and POH is a constant, is equal to 14 at 25 degrees Celsius. Okay, so you need to memorize that as well. Now, I've seen I've noticed that many students know the pH scale basically from this simple chart here, that if it's less than 7, it's called acidic. If it's equal to 7, neutral. If it's greater than 7, it's called a basic solution. All right, so let's move to the next slide. Now, in the beginning of the lecture, we referred to Arrhenius' definition of acid and bases. Now, this is another definition of acid and bases, which is called the Bronsted-Lowry acid-base definition. Bronsted and Lowry, their name of two scientists who came up with the definition that you have here on this page. So, according to Bronsted-Lowry definition, acid is a proton donor and a base is a proton acceptor. And by proton, we mean H plus ion, hydrogen ion is the proton. Now, so according to the Bronsted-Lowry definition, acid-base reaction is basically a proton transfer reaction because acid is donating the proton, and of course, base is going to accept the proton. So it's basically H plus ion that is being exchanged between the acid and the bases. So it's a H plus or proton transfer reaction. Now, another concept that we need to be familiar with, and we are going to refer to this in the concept of acid-base equilibria, is called conjugate acid-base pair. Now, if you look at this simple, typical weak acid reaction or weak acid ionization, that the HA, which is the weak acid, ionizes into H plus and A minus. By the way, in the context of acid-base equilibria, I keep referring to ionization and dissociation. They are the same thing. So when I say HA ionizes, meaning producing ions on the right-hand side, or HA dissociates into H plus and A minus, they're basically conveying the same meaning. Okay, so in this reaction that you've seen before, HA is the typical acid, H plus is the hydrogen ion released by HA because, again, acid is supposed to be a proton donor, and A minus is the conjugate base that is formed after HA releases or gives up the H plus. Okay, so we call that the conjugate base of the acid. So the HA slash A minus together is a pair, which is called the conjugate acid-base pair. So this is the acid, which has the hydrogen, and this is the base, which is now has basically when the HA loses the hydrogen and becomes A minus, then that combination is called the conjugate acid-base pair. Now, I am going to basically refer to A minus or anything that has negative charge as a base. And we will talk about this shortly on this lecture slide, that HA is the weak acid, A minus is the base that is formed from the weak acid, but by contrast, it's typically a strong base, okay? So if HA is a weak acid, it loses the proton or the H plus to form A minus, but the A minus that is formed is now a strong base. Okay, so let's keep that in mind. We usually consider the cations or positively charged ions to be acidic compared to anions or negatively charged ions, which are basic. So anything carrying a positive charge, acidic. Anything carrying a negative charge, considered to be basic. That's what we are basically trying to say here. Okay, now for any conjugate acid-base pair, for example, HA, A minus, we can write that Ka times Kb is a constant, is 1 times 10 negative 14, which we saw this in basically previously when we wrote the Kw for the autoionization of water. So this 1 times 10 negative 14 pops up quite frequently in acid-base equilibria. Now this equation, equation 5, which you need to memorize, is only for conjugate acid-base pair, okay? So if the acid and the base are not related through a conjugate acid-base concept, then you cannot write that for them. In other words, this Ka, if it's for HCl, and this Kb it's for NH3, we cannot write this equation because they are not related as conjugate acid-base pair. Okay, so I have also given you the definition. Ka, one more time, is acid dissociation, and Kb is the base dissociation constant. All right, so let's move on to the last lecture slide for today, and that is the conjugate acid-base pair is not only limited to the reaction of acids, but also you can write it for a base reaction. For example, ammonia, NH3, which is a weak base, reacts with water, and then it produces NH4 plus OH minus. The reaction is at equilibrium. It's a weak base reaction. And remember, we talked about weak acids and weak bases establishing equilibrium when they react or when they dissociate. So the NH3 is a weak base, so therefore accepts a proton. The source of the proton is water. It forms a conjugate acid, NH4 plus. So basically, H2O releases a hydrogen. The base NH3 accepts it. It becomes NH4 plus and OH minus. Okay, so the NH4 plus now is the conjugate acid of the weak base NH3. Okay, so NH3, NH4 plus, now they are called conjugate acid-base pair. You can actually summarize this whole concept of a conjugate acid-base pair by saying that a conjugate acid-base pair is any pair that differ by the presence or absence of what? Of H plus. Okay, so for example, what's the difference between NH3 and NH4 plus? You know, it's basically H plus, because H plus has been added to NH3 to form NH4 plus. Okay, and also we can write the Ka times Kb equal to 1 times 10 negative 14 equation one more time for this. So, but this time the Ka refers to NH4 plus, the Kb refers to NH3, and therefore that is equal to 1 times 10 negative 14. So I'm going to stop right here for today's lecture, but I also want to give you the end of chapter problems that I promised you last week on Thursday when we had that virtual classroom meeting. So I have listed the problem numbers at the end of chapter 17. Number 16, number 30, 36, 42, 46, 48, 50, 52, 54, and 66. So again, these are the problems at the end of chapter 17. This is just for you to get some idea about the type of problems that you should focus on, and you don't need to turn them back into me, okay? So this is just for your own information. Okay, well, I'm going to sign off here, and enjoy the rest of your day. I will see you this Thursday. Please make sure you go over the information that I've given you so far, and yeah, if you have any questions, let me know when we meet again on Thursday. Have a great day. See you later.